Hi everyone! So we have finished sessions 4.1 to 4.7. Let's make a review. Please go to our final review notes that you can download from our course websites. Let's look at Chapter 4. So Chapter 4 is about applications of derivatives. So 4.1, we talk about how to find absolute maximum and absolute minimum on a closed interval. How do we do that? First, we want to find the derivative, and then we find the critical points, i.e. we set the derivative is 0. If the derivative is a quotient, we set the numerator is 0 and the denominator is 0 to find the critical points. Okay, and then we plot the endpoints of the interval into our function, and we plot the critical points into our function, and then we compare them. So among those values, the biggest is the absolute maximum value, and then the smallest is the absolute minimum values. Okay, everybody? And then in session 4.2, we talk about problems like find intervals of increasing and decreasing, find local maximum and minimum. Okay, and here are the steps. First, we take the derivative and we find critical points, and we try to factor the derivative. Okay, and then we consider the domain of the function, and then we draw the diagram. Remember, we have the domain, and then it's separated by those in critical points. Okay, so we have the domain separated by those critical points, and you figure out on each intervals where our f prime, we want to answer is it positive or negative, and for f, we want to answer is it increasing or decreasing. Okay, and at the critical points, you always either get 0 or does not exist. Okay, for the critical points. And next, we also talk about problems finding the interval of concave up and concave down and the inflection points. So inflection points, what are inflection points? So the big difference between critical points and inflection point is critical points is where the is in the domain, and it's either the first derivative is 0 or the first derivative does not exist. Inflection point is first is in the domain, and either the second derivative is 0 or the second derivative does not exist, plus one more condition. The second derivative must change sign. Okay, that's the inflection point. So here the first step is find the second derivative, and we factor it completely, set it equal to 0 and solve for x. Sometimes if the second derivative is like a quotient, then you set the numerator is 0 and the denominator is 0 to find all the possible inflection points. And then we look at the domain. Depending on the domain, we draw the domain, and then it's separated by those important points. And for f prime prime, we want to answer like plus or minus. For f, we want to answer like concave up or concave down. Okay? And we also have a type of problem where I ask you to sketch the graph. So this is a longer problem. We're going to find the first derivative, and we find the critical points. Then we find the second derivative, we find the possible inflection points, and we want to get factored form. Then we want to look at the domain, and then we want to draw a combined table. So this combined table has f prime, and f. So the domain is separated by the critical points and the possible inflection points. Okay, and you know, for f prime, we want to answer like is it 0 on the critical points, or it does not exist on the critical points? On those intervals, do we have plus or do we have minus? For the second derivative, we do the same thing. So on the roots of where you find you set the second derivative is 0, so those will be zeros. And then how about on the other values? Is it positive or negative? Okay, and then for f, what do you want to fill in? You want to fill in one of those four shapes of a circle. If it's increasing and concave down, then we have this shape. If it's decreasing concave down, we have this shape. If we have decreasing concave up, we have this shape. And if we have increasing concave up, then we have this shape. Be careful, don't draw me parentheses or S. Okay, I should be able to tell whether it's increasing or decreasing, whether it's concave up or down. Then you're going to plot all the important points. The important points, I mean the critical points and the inflection points. Okay, so plot it on the graph, and then finally connect those points using those pieces. Those pieces is actually the exact shape of the graph. Okay, and then we talk about sections 4.4 optimization problems. Here are the steps. First, you want to sketch a picture, name the variables. So you want to figure out what is changing, set the variable x, y, or a for area, v for volume. And then you want to ask, what is constant? If it's constant, don't name a variable. Just give it a number, because you give it a number, you know it's not going to change. When you differentiate it, the number is just going to be 0. Okay? So don't make too many variables. And then we also need to figure out what to be optimized, such as maybe we want to maximize the volume, we want to minimize the surface area, okay? So this is the thing that you want to differentiate in the future. Second step, we want to write relations. We want to express our unknown quantity, which is the thing we want to optimize, as a function with one variable. So we only learned one variable calculus. We haven't learned multivariable calculus. That's calculus 3. So there should be enough relations in the problem such that you can express the unknown as a function with one variable. And then we can differentiate this unknown quantity and respect to x, okay? Or maybe your variable is r, or so we know it's a function of one variable. You can take the derivative, and then you can find the critical points and domain. So domain is so important, because sometimes you might have couple critical points, but only some of them lies in the domain. Okay, and then you draw the diagram to verify is a maximum or minimum. So usually the problem already tell you, because they ask you like maximize the volume, then you expect your answer should be a maximum, or the problem is asking you to minimize the time, so you know the answer you get should be a minimum. Okay, so here you just verify, check whether your answer makes sense agrees with what the problem is asking. Okay. And then in sections 4.5, we talk about linear approximation. So here are the 4 steps. The first step, you're going to define your function and find the number a. The number a is a good number that is close to our x. X is 65, okay? So close to 65, and you can calculate f of a and f prime of a easily. Okay, so that's why here we pick a to be 64, because we know the square root of 64 is 8. Okay, I mean the square root of a is an integer. So f of a in this case is going to be 1 over 8. Okay, so a second step, we find the derivative, we plug in a. Okay, so in this process, you should be able to calculate the number without a calculator. Okay, the third step, use the tangent line equation. So that's the y value, f of a, plus the slope, f prime of a, times x minus a. And the last step, well, our function f of 64 is approximately equal to, you plug in x is 64. So don't plug in x the whole thing. That's not x. Usually x should be just an integer, okay, or a number, okay? Because if you know how to calculate 1 over square root of 64, you don't need linear approximation, right? If you know it, you don't need it. You don't need a linear approximation. You can just calculate it, okay? So yeah, so we plug in the ch4 into this tangent line equation and we get a number. You can always check your answer by plug this guy into our calculator. If our result are close to the answer we get here, then we're doing good. But if the results are not close, maybe you pick a wrong A, or maybe your derivative is wrong. So go back and check your work in that case. All right. How about 4.6? So 4.6, we talk about intermediate value theorem. We also talk about the mean value theorem. So the typical problem is to show an equation has exactly one root. So a lot of steps are the same except some part of it. Okay, so you replace this part when you see a new function and at least one root. You say f is continuous and you want to plug a number such that f of that number is negative and you need another number, f of that number is positive. And then you can say by intermediate value theorem, there is a c such that f of c equals to 0. So f has at least one root. For the at most one root, you know f is continuous. To figure out f is differentiable, you gotta take the derivative of f. And usually it's either always positive or it's always negative. Okay, and then we can use we can prove by contradiction. Suppose what we assume is wrong, which is suppose we don't have at most one root. So that means suppose we have two roots, a and b. So f of a equals to f of b is 0. Then by mean value theorem, there is a c such that f prime of c equals to 0. So you can say this is by mean value theorem, or you can say by Rolle's theorem. They're same. Rolle's theorem is just a special case of the mean value theorem. Okay, so this is we get f prime of c equal to 0. This is a contradiction to the fact that the derivative is always positive for our problem. Okay, so some other problem could be negative. Okay, so no matter it's always positive or not always negative, we have a contradiction with the derivative is 0 somewhere. Okay, so because we have a contradiction, it means whatever we assume is false. So f cannot have two roots. So f can have at most one root. And then combine those two cases, we know the equation has exactly one root. And the second type problem is you show the functions satisfy the condition of the mean value theorem, and you want to find the points which guarantee to exist by the mean value theorem. So please look at sessions 4.6 notes for more detail. Okay, 4.7, L'Hopital's rule. Okay, L'Hopital's rule tells us that if we have a quotient, and if we get 0 over 0 or infinity over infinity, then we can use L'Hopital's rule, and that is the limits of the derivative of the numerator over the derivative of the denominator. If the limits on the right hand side exists, or it could be infinity or minus infinity. Okay, so we have the indeterminate form 0 over 0, infinity over infinity, and 0 times infinity. In that case, you just move one factor into the denominator, but don't forget to flip it. Okay, you cannot just move the sine x here. You have to flip it so it becomes 1 over sine x. And usually when you see a trig function and a natural log, you move the trig functions. When you see a power function and a natural log, you move the power functions. Okay, so you don't move the natural log usually. And we also have the infinity minus infinity form. What you do is if you see a difference of two fractions, you take the common denominator and combine into a single fraction. Because our goal is to transform those types into infinity over infinity or 0 over 0. So we hope to see a quotient. Okay, everybody? Okay, and for those three types, where we have infinity to the 0, 0 to the 0, 1 to the infinity. We have 4 steps. First step, let y be the function. Second step, apply natural log on both sides. And bring the power in front. Okay? And because our goal is to create infinity over infinity or 0 over 0, so you also like to move the factor in the denominator. Oh, here is already a fraction, so let's just write it better, okay? And then step 3, we want to compute the limits. So in this process, you may use L'Hopital's rule. And the fourth step, the limits of our function equals to e to the whatever answer we get from step 3. Okay, so compare this with the logarithmic differentiation. Many students make mistakes and get confused between them. So I hope you can review the logarithmic differentiation and then you can see the difference between them. Okay, what is the difference between them? You don't remember? Okay, so the first step and second step are the same. But the third step, you're going to do implicit differentiation. So you're going to differentiate the both sides. The left-hand side, you always get 1 over y times y prime. And the right-hand side is going to be maybe a combination of product rule, chain rule, and quotient rule. Okay, and at the end, you want to find y prime. So y prime is just going to be your right-hand side times y. What is y? Your original function. Okay, so that's the logarithmic differentiation. And so this is what we're going to test about on exam 3. So exam 3 covers 4.1 to 4.7. So 4.8 and the rest is just going to be show up in the final exam. Your final exam is cumulative, everything. Okay, so that's why I can allow you to use your final exam to replace one of the lowest midterm exam. Okay. So after the review, I want to do more exercise with you. So let's do this kind of exercise. You're given a piecewise function. We want to find the parameters such that part A, the function is continuous. Part B, the function is differentiable. Okay, we didn't do many of these examples. So let's do more here. To find the values such that f is continuous, we look at the left-sided limits. First of all, those two pieces met at 1, okay? So f is continuous on those two pieces. So the only problem f might not be continuous is when the two pieces met. Do they meet at the same point? Yeah, then it's continuous. Do they meet at the two different points? No, then there is a jump discontinuity. Okay, so we want to make sure they meet at the same value. Okay, so the left side limit of f, and we also want to compute the right side limit of f. The left side limit of f, we have, okay, which one, which piece? The top piece, right, is the left because it's less than equal, so that's the top piece. So e to the x minus 1 plus 2. And then when we plug in 1, we get e to the 0 plus 2. Well, that's 1 plus 2, which is 3. Okay, and on the other side, we have the bottom formula because it's x greater than on the right-hand side. Okay, so ax squared plus b cosine x minus 1. So we plug in 1. 1 squared is 1, so a plus b, cosine of 1 minus 1 is 0, cosine 0 is 1. So the answer is a plus b. And don't forget, in order to show continuous, you need the left side limit equal to the right side limit equals to the function value. So what's the function value? You're looking for where do you have the equal sign. So this piece is f of 1. Set them equal. So you can say if a plus b equals to 3, then f is continuous. All right, so that is part A. How about part B? Well, part B, we want to find the values of A and B. The function is differentiable, so instead of looking at the left side limits or right side limits of f, we want to look at the left side derivative and right side derivative of f. So left side derivative and the right sided derivative. Okay, so the left sided was the function e to the x minus 1 plus 2. E to the x minus 1 plus 2. And we want to differentiate. How about the right side? We have ax squared plus b cosine x minus 1 and prime. Okay, let's see what is that. So the first one, we take the derivative. E to the x minus 1 derivative is e to the x minus 1 and times x minus 1 prime, which is 1. And let me write it down. Derivative of 2 is 0. So this is the same as e to the x minus 1. And when we plug in 1 in it, we get e to the 0, which is 1. Do you get the same answer, everybody? All right, let's look at the other side. So we take the derivative. Derivative of ax squared is 2ax. Derivative, so b and a are just constants. Constant multiples stay here. Derivative of cosine is minus sine. Okay, so minus sine. And u prime, but here u prime is 1. Okay, so just leave it like that. Now let's plug in. We plug in 1. Oh, so we're actually going to plug in, so we don't need limits. Okay, we plug in 1. We have 2a. Here we plug in 1. 1 minus 1 is 0. Sine 0 is 0, so that's 0. So we get 2a. Oh, what happened? We set them equal. So we have 2a equals to 1. A is 1/2. And keep in mind, to be differentiable, the function must be continuous first. So whatever condition we have from part A, also we need to put it here. So a plus b is 3. Then what is b? b is 3 minus a, so 3 minus 1/2, which is 5/2. So we answer the problem like, if a is 1/2, b is 5/2, then f is differentiable. Okay, so that's the complete solution of this problem. Okay, let's look at example 2. So I hope you can pause the video here and try to work on this problem first. Okay, because for math, practice is very important. All right, have you done? Let's check our answer. So part A, continuous, we need to look at the left side limit and the right side limit. The left side limit is this guy, right? So we put it here. 5bx squared minus 3. We plug in x is 1. So we have 5b minus 3. Alright, how about the top guy? The top guy, we have x goes to 1, a square root of x, ln of x plus b. And when we plug in x as 1, ln of 1 is 0. So this is just B. Okay, and which one is equals to f of 1? Look at this guy. This guy. So is this one, the left side limit, also equals to f of 1? All right. So, and then we can continue to set them equal. So we have 5b minus 3 equals to b. Subtract b on both sides. 4b, move the 3 over, is 3. So b equals to 3 over 4. So sometimes you might get b is a number, but here like a can be anything. So sometimes, like the previous problem, you don't get b is a number, you just get a and b a relation among them. Okay? All right, so let's continue. So continue part B. For differentiable, we need to compute the two-side derivatives. Okay, the derivative of the top, what's the top? 5bx squared minus 3. Well, that is, what is that? Derivative of, so 5b stay there. And then derivative of x squared is 2. Derivative of 3 is 0. So we get 10b. How about the other side? We have a, well, square root. I know we're going to take the derivative. So I'm going to rewrite square root to be x to the 1/2. So when I take the derivative in the next step, it's more convenient. Okay, so we want to differentiate this guy. Okay, so it's a product of two things. We need product rule. All right. So a stay here. Then the derivative of the first guy times second guy plus first guy times the derivative of the second guy. Well, derivative of b is just 0. Okay? Let's continue. So we have a derivative of x to the 1/2 is 1/2 x to the minus 1/2 times ln of x plus x to the 1/2, and this is derivative of ln of x is 1 over x. Okay, so what do we get? So here we get, we plug in 1, but ln of 1 is 0. So this is, the first guy is gone. And the second one, 1 over 1 is 1. So the answer is just A. Okay, so let's see. We set them equal. Then b equals to a, but do we have something? So b, well, b is 3 over 4. Then 10b is 10 times 3 over 4. We can factor out the 2. We can cancel the 2. 3 times 5 is 15. So 15 over 2 is our answer. Okay, everybody? So that's why we get if a is 15 over 2, b is 3 over 4, then f is differentiable. Okay, so that finished the problem. Okay, so feel free to ask me more questions during our online office hours. Bye!